This video is on the acidity of complex ions. In this video we're going to go through defining Lewis acid and Lewis base, understand what is meant by a metal hexacrine ion, understand what affects the acidity of hexacrine ions, describe and explain the test tube reactions between metal ions and hydroxide ions, ammonia and carbonate ions, understand what is meant by amphoteric, and know the chromate and dichromate equilibrium. So there are two different ways you can think of acids and bases. The one that you've come across before already is the more common description, and that's the Bronsted-Lowry description of acidity, which is where acids are proton donators, so H plus donators, and bases are proton acceptors. The problem here is that this doesn't explain why compounds that do not contain hydrogen can be acids as well. So the other description of acids is known as the Lewis theory, and Lewis acids, instead of donating protons, accept electron pairs. So Lewis acids accept electron pairs, and Lewis bases donate electron pairs. Which means that when we're forming complexes, the ligands are Lewis bases because they're donating electron pairs to the complex sign in the middle, which is acting as a Lewis acid. So before we can move on to the to why the acidity of complex ions changes, we need to first understand what a metal hexacrine is. So I have covered this in other videos, so I'll just cover it quickly in this one. So a metal hexacrine is basically a central metal ion, which I'll just give a symbol M, surrounded by 6 water ligands, all bonded through the oxygen. Like so, and they're datively bonded, so we'll complete it properly with arrows. And this will this will have the charge that is on the central metal ion. So I'll just give a question mark there, because the charge on the overall ion will depend on the charge on the central metal ion. And usually that's either 2 plus or 3 plus, and it's that charge that affects the acidity of this hexacrine complex ion. So for us to explain why different hexacrine complexes have different acidities, we need to take an example of 2 complexes, and the basic reason is due to the oxidation state of the central metal ion. So here we've got 2 hexacrine complexes, one with iron 2 plus in the middle and one with iron 3 plus in the middle. Now the iron 3 plus is going to be far more attractive to electrons than iron 2 plus, and so what happens is that the electrons are pulled through the bonds that are being formed with the iron. So the iron 3 plus pulls electrons through this dative bond that is formed with the oxygen, and therefore the oxygen needs to pull electrons from the H through this bond, which then weakens this bond. And so what happens is this H plus ion is readily freed, if you like, from the complex ion. So basically what happens is the following mini mechanism, if you like. So the electrons in this would go here, and the electrons here would go in here, and what you get essentially happening is the following reaction. You will get the following equilibrium set up where you've got Fe H2O 6 3 plus in equilibrium with Fe H2O 5OH 2 plus overall plus H plus. Now the 2 plus version of the hexacrine won't do this because the 2 plus charge isn't as attractive to the electrons and therefore it doesn't weaken the OH bonds. So, how does this affect test tube reactions between these metal ions and different things? So, basically what you've got to think to yourself is when we are reacting different substances with complex ions, will the substance act as a base or will it act as a ligand? So you're either going to get an acid-base reaction or you're going to get a ligand substitution reaction. So if we use iron to start with iron 2 plus, so iron 2 hexaraqua, with OH minus, the OH minus is always going to act as a base because it is an alkali. And so what happens here is we get the iron hydroxide, so FeH2O 4OH2 and 2 waters. And exactly the same thing happens for iron 3 plus. So whenever you're adding hydroxide to iron, the same thing happens. It's just that your final compound, sorry, I should add 2 OH minuses here, the final compound is going to be different because you're going to have different number of hydroxide formed. So iron hydroxide with a 3 plus oxidation state will have 3 hydroxide ions and 3 waters. Now this is a green precipitate and this is an orange-brown precipitate. If you then look at ammonia with iron, you get very similar things happening. NH3 will also act as a base with both. So you have FeH2O 6 2 plus and you have FeH2O 6 3 plus 2 ammonias in the first case and 3 ammonias in the second case, and the ammonia is going to act as a base, so it's going to grab an H plus off these. So you'll also form the hydroxides, so that should be in 4, and the hydroxide on the bottom. And then what else is formed is the ammonium ion, so the NH3 with an extra hydrogen, so NH4 plus, and on the bottom as well. Now with carbonate ions we then get 2 different reactions. With a 2 plus oxidation state you're going to get a ligand substitution reaction because it's not going to be acid-base because the 2 plus ion is not acidic enough. And with the iron 3 plus complex you're going to get an acid-base reaction. So with iron H2O 6 2 plus with carbonate ions which are CO3 2 minus, here you're going to get a ligand substitution reaction. So you're going to make iron carbonate and you're going to make 6 waters. However, with the 3 plus ion you get an acid-base reaction. So what you'll form is the hydroxide ion, so FeH2O 3OH3. You'll form 3 waters and you'll also form carbon dioxide. And we'll also need to balance this by putting 3's in front of the carbonate ions and the carbon dioxide. So what's important to take away from this slide is the carbonate reaction. So if it's a 2 plus ion, you'll always get the ligand substitution reaction which forms the carbonate. But if it's a 3 plus ion, you'll always get the acid-base reaction which forms the hydroxide and water and carbon dioxide. So we've been talking about things that can act as acids. The term amphoteric describes the idea that something can act as an acid and as a base. So a compound that will react with acids and a compound, and therefore acting as a base, and a compound that will also react with bases and therefore be acting as an acid. An example of this type of compound is aluminium hydroxide, which has the formula AlH2O3 OH3, and that will react with, for example, hydrochloric acid to form, so let's move that across, to form aluminium with 6 waters around it, so the hexacrine, with a 3+ charge and 3 Cl-. So here, the aluminium hydroxide has acted as a base, as you'd expect from a hydroxide, to form the hexacrine and 3 chlorides with hydrochloric acid. However, the aluminium hydroxide will also react as an acid. So if you react it with some OH-, it will then give a colour solution of tetrahydroxyaluminate, which has the following formula. I'm sure you're all aware of it from revising. So if you add more OH-, so this is excess OH- to the aluminium hexacrine, you form the following complex, which is a coloured solution, and 3H2O. So here we've got it acting as an acid, and here we've got it acting as a base. Another hydroxide that will do this is chromium hydroxide. So again, as a base, we've got chromium hydroxide, H2O 3OH3, adding to, for example, hydrochloric acid again we'll choose, and that will form the same Cr hexacrine 3++3 chlorides. So that's acting as a base, and then you can also get it acting as an acid with more OH- this time, because what you form is CrOH6 3- plus 3H2O. So again, we've got the chromium hydroxide here acting as a base, and here acting as an acid, and therefore it is amphoteric. Now, the chromate-dichromate equilibrium is actually important in a couple of the other videos that I've made. I'm just going to make it explicit in this slide. So basically, depending on the conditions, chromate and dichromate will form. So you've got chromate, which is CrO4-, not 2-, sorry, and this is in equilibrium with the dichromate ion, which is Cr2O7 2-. And to turn the chromate into dichromate, we can add acid. So if we add 2H+ to this side, we'll then form the dichromate ion and a water molecule. And this shows why you need to use acidified potassium dichromate when you oxidize alcohols, because if you acidify the potassium dichromate, that will shift or force this equilibrium to move to the right-hand side, making sure that all your chromium is in the form of dichromate rather than chromate. If you have alkali conditions, then the H+ ion will react with the OH-, forming water, and the removal of the H+ will force equilibrium to the left-hand side, forming more chromate ions. So this side is favoured by alkaline conditions, and this side is favoured by acidic conditions. So it's important you look at what the conditions are when you're considering the form of the chromium, just to make sure you're writing the correct chromate or dichromate ion. So let's just have a look at a few past exam paper questions. So in its reactions with transition metal ions, ammonia can act as a Bronsted-Lowry base or as a Lewis base. Define the term Lewis base. So a Lewis base is an electron pair donor. And it says, write an equation for a reaction between aqueous copper-2 ions and ammonia in which ammonia acts as a Bronsted-Lowry base. State what you would observe. So a Bronsted-Lowry base is a hydrogen, a proton acceptor. So this is where it's acting as the more traditional base that you learn in your lower school. So you're going to have Cu, H2O, 6, 2 plus your ammonia, NH3, and that will form, the NH3 will grab H pluses from the water, so you'll form Cu, H2O, 4, OH2, plus 2 NH4 plus. And you need 2 ammonias to do that. So that's the ammonia grabbing H plus from the copper hexacrine. And it says state what you'd observe while you're going from a blue solution to a blue precipitate. In this case, the blue solution being your copper hexaqua and your blue precipitate being your copper hydroxide. Then it says, write an equation for a different reaction between aqueous copper-2 ions and ammonia in which ammonia acts as a Lewis base but not as a Bronsted-Lowry base, and state what you'd observe. So here, the ammonia is going to partake in ligand substitution. And if you've learned your table, you'll know that when copper hexaqua reacts with ammonia in a ligand substitution reaction, and this is excess ammonia in your table, then what you'll form is copper with 4 ammonias and 2 waters. Still has a 2 plus charge because the ammonia is also neutral. You need 4 ammonias on this side, and you'll also have 4 waters on this side being kicked off. And it says, state what you'd observe, you're going from a blue solution to a deep blue solution. And that word deep is very important to distinguish between the types of blue. And then diaminoethane, like ammonia, can act as a base and as a ligand. Write an equation for reaction that occurs between an aqueous solution of aluminium chloride and an excess of aqueous diaminoethane. Describe the appearance of the aluminium-containing reaction product. The fact it's an aqueous solution of aluminium chloride means that it's the aluminium hexacrine that you're starting with. The chloride ions are simply counter ions, if you like. They're there to balance the charges. So it's the hexacrine that's reacting, and remember aluminium has a 3 plus charge, which means that this diaminoethane will act as a Bronsted-Lowry base, grabbing H pluses from that water. So this would be an acid-base reaction, if you like. So this will react with H2N, CH2, CH2, NH2, and that's going to form your aluminium hydroxide, Al H2O 3OH3, and is also going to form 3 H2N CH2 CH2 NH3 plus ions. So that's where this diaminoethane has grabbed an H plus from the water to form this hydroxide and this ion, which is like an analogue of the ammonium ion that's formed in the previous slide. And then this, because it's aluminium and not a transition metal, is going to be white, and because it's the hydroxide and has no charge, it's a precipitate. So a white precipitate is the appearance. And then this question is from an old spec paper. I couldn't find any amphoteric questions, any new ones, which suggests it may come up. So it says, write equations for 2 reactions which together show the amphoteric character of aluminium hydroxide. So you've got Al H2O 3OH3. That's the aluminium hydroxide. So acting as a base, you've got it reacting with an acid. So we'll react with HCl as we had in the previous slides, and that forms the aluminium hexacrine plus 3Cl minus, and you need 3HCl to do that. And then as an acid, the aluminium the aluminium hydroxide reacts with OH minus to form the following complex and water. And we need to balance that by putting a 3 in front of the water.